students, welcome once again to Physics Lab. We are going to perform a beautiful experiment, meter bridge. This experiment is based on a very important principle, Wheatstone bridge principle. Scientist by name Wheatstone in 1842 invented this particular Wheatstone bridge principle, and we will learn today about it. So, here you can see P, Q, R, S are the four resistances connected in the shape of a quadrilateral or a parallelogram, and in the center between B and D we have connected a galvanometer, and between A and C we have connected a primary circuit. It contains a cell or a battery, key K, rheostat resistance RH. So we can control the current with the help of rheostat. To start with, remember one thing, we need to put on this key first. When we put on the key, current I starts flowing from here. It comes through this and comes near a junction. So directly the whole current comes towards the junction. At this junction, it gets divided. Suppose I say I1 current flows in this branch, then I minus I1 will flow in this branch. Now this current comes here, and then some part of the current goes here, some part of the current goes here. Similarly, this current comes here, and the current which has come this side will join this, and it will be coming here. Now this Ig current, which is the current in the galvanometer, it all depends whether it will come from here to here or here to here. It all depends on the potential VB and VT. But Wheatstone bridge principle, it states that for a balanced bridge. Now what is meant by balanced bridge? Let's learn. So for a balanced bridge, Ig current is 0. Ig current, that is the current flowing through the galvanometer, is 0. If that is the condition, then he comes to this conclusion, P upon Q is equal to R upon S. What is P? Resistance in the first arm. Q is the second arm. R in the third arm. And S in the fourth arm. And what we can do? We can find out one unknown when there are four resistances given. Three are knowns and one is unknown. With this relationship, we can find out what is the unknown. In this case, suppose S is unknown to us, and you know P, Q and R, we can find out S with this relation. Now, that is what is the statement of the principle. Let's prove it. Here is the potential V, potential difference across the cell V. So if this is V, this has to be 0. Suppose we take a number. So we won't take a number at the moment, we will just call it V. So potential at this point is V, the current starts flowing. Current I is flowing, coming at the junction A. Then because of junction rule, it gets divided into two parts. Suppose I1 comes here, then I minus I1 goes in this direction. This is I. I1 has gone here, I minus I1 comes here. You know very well that these two are at the same potential, so no current is flowing in this galvanometer. So no current will flow, means the whole current I1 will start flowing in the branch Q. The whole current I minus I1 will come here till this C point. Now look here, they will again get added up. So I1 plus I minus I1 plus I minus I1 will become I1 and I will cancel. So what remains is I. So the I current comes back to the battery. Okay, that means the rule of the battery is whatever current it gives out, the same current has to come back to the battery. It is principle of conservation of charge. Now this point is very clear. Now let's solve this equation. This potential at this point is VA minus potential at this point is VB. So potential drop in this branch VA minus VB is by Ohm's law current I1 into P. Similarly, potential at V minus D. Now VA minus VD will be I minus I1 into R. R is the resistance, I minus I1 is the current, again Ohm's law. And they are equal, so I1P is equal to I minus I1 into R. So this is the equation number 1. Now, let's go here. VB minus VC, you can say VC minus VB, it's all the same, we are only taking the drop. So, VB minus VC, we can write it as I1 into Q. Similarly, VD minus VC is equal to I minus I1 into S. Now, both are equal. VB is equal to VD. Therefore, this potential drop is equal to this potential drop. Both are equal. So, what we can do is, we can write, we'll rub it out to this part, and we can write I1Q is equal to I minus I1 into S. So, this is my equation number 2. Equation number 2. Now, what we can do is, we can divide LHS and RHS from both the sides of equation 1 and 2, and we can write here I1P divided by I1Q is equal to I minus I1 into R upon I minus I1 into S. What have we done? We have divided equation 1 by equation 2, left hand side, right hand side. So what happens now? What do we get? Can you see? I1 and I1 cancels. I minus I1 cancels. And what do we get? P upon Q is equal to R upon S. We get this relation. So we got the relation. Now, what is this called as? What kind of condition? It is called as balanced bridge. And what is the condition? Current in the galvanometer is 0. Instead of galvanometer, if I connect one resistance wire here of say 1 ohm, nothing will flow in that 1 ohm. It is as good as not there. So if this condition, now for example, if P upon Q is what R upon S, let's take for example. Suppose this is 2 ohms. This is 2, this is 4. This is 4 and this is 8. Now let us consider this example. 2 upon 4 is 1 by 2. 4 upon 8 is 1 by 2. Therefore, nothing will flow in the galvanometer. We have reached a balanced condition. Vice versa, if P upon Q is equal to R upon S, proves that Ig is 0. Vice versa. And therefore, can you find out the calculate and find out the value? 4 plus 2, 6. 4 plus 8, 12. 6 and 12, it is in parallel. Find out the value 6 into 12 upon 6 plus 12. So, this relation, these problems we have already solved in the class. So, now we go to the main part of this. Now, what is meter bridge? Meter bridge is based on the principle of Wheatstone bridge network, Wheatstone principle. Now, we will learn how to perform this experiment. So, let's learn about the concept of meter bridge. You can see here, these are the metal strips, L-shaped. In between there is one metal strip, another L-shaped, and there is a wire which is fixed. This whole arrangement is on wooden plank. A and C are the binding screws at the end point, are the end points of the wire. As the name says, it is meter bridge because this wire is 1 meter in length, 100 centimeter. Second thing, here you can see there are binding screws. So you can see here, this is A, this is a metal strip which is one connection. So if this is A, this is A, this is A. This is B, so this is B and this also is B. This is C, so this is C and this is C. So this is the actual construction. There is one gap here, there is another gap here. In this gap, we connect unknown resistance. We don't know the resistance of that particular resistor. So we have to call it unknown. Whereas this is known. Here is the resistance box. It's a resistance box 0 to so many ohms, 500 ohms. We can take resistance box. And here this particular galvanometer is connected between B and this point is D. And this is the jockey. This is the jockey. So now you know. And main point is primary cell. Primary cell means there is one cell here. Now we have taken a Daniell cell because it's a very small voltage. We don't want high currents here. So we have taken a Daniell cell. Then there is a key and there is a rheostat to control the current. We don't want excessive current because ultimately that current also is going to pass to the galvanometer, and a very sensitive galvanometer. So let's compare this bridge with this bridge because both are same. Both are same. Let's compare. Look here. Here is X. I'll draw here. Here I draw. This is point A. This is point A. Here is the point A. Between A and C, there is a primary circuit. Can you see that? So this is point A. A then goes to X. Here A goes to P. So instead of P, we have called this X. Then this is my B point because A and B we have connected X. Between B and C, we have connected a resistance box. So this resistance box is here. Resistance box. That is connected B and C. Now, here there is a wire. Okay. Now this wire has some length and it is metallic wire. By the way, do you know what this wire is made up of? It is made up of a material called constantan or manganese. Constantan has very low temperature coefficient, negligible. Alpha is very low. What is the meaning of that? If you pass a current for a long time in this wire will get heated up. And due to heating, the resistance of that wire may change if it is a metal. But this is a metallic alloy, constantan and manganese. What is its property? Its resistivity or specific resistance is very high. So it does not allow large current to flow through it. Point number one. And point number two, even if you pass a current for a long time, even if the wire gets heated up, the resistance of this will not change. Resistance of the wire will not change, negligible. It's negligible. So this is the property of constantan or manganese. Many times this question is asked, why is constantan used to make a metal wire for meter bridge? Then you have to answer this question. So this is another story. Now, if this is a wire, it has some resistance. Now the resistance of this portion, now the galvanometer touches here. So resistance of this portion I call it RAD and resistance of this portion I call it RCD from here to here. Now RAD is the resistance between A and D. So resistance between A and D, so I write here A and D. What is this resistance? RAD. And what is the resistance between D and C? This is C, this is D. It is RCD. So here we will change on this circuit. Is it not the same one? What is missing by the way? Galvanometer. It is connected between B and D. So this is my galvanometer. Connected between B and D. So this is exactly a meter Wheatstone bridge, only in different modified form. Now, so I will do one thing here. I will write here X. I will write here. What is this? Resistance box R. Here I will write RAD. And here I will write RCD. RCD. Now, what is said? Now we have to perform the experiment. Let us remove. Now we don't know this. So first we'll start with 10 ohms. Suppose I remove 10 ohms from here. When I remove 10 ohms from here, I take the jockey and connect it at this point. It is at a higher potential. So the current is flowing from here. This way the current is flowing. Yes or no? If the current is flowing from here like this, you get one side deflection. So we get the deflection in the galvanometer on the left. Now we can control the current. Suppose it shows very less deflection, 10. We don't want. We have to make it full scale. What should we do? We would adjust the rheostat and make it full scale deflection on left side. Then what I do? This is higher potential and this is the lower potential. I touch the jockey here. Then I will get deflection on this side. On which side? On the other side. Now for 10 ohms, say 10 ohms I have removed, I find that it is not moved that much on the other side. It is small deflection. So what I do is, I just take the jockey and I start moving. You know that when I touch A point, you get left side. When I touch C point, I get right side. So this is a road, left and right. So in the middle, somewhere, I am going to get zero deflection in the galvanometer. So we go on tapping. By chance, I get the null point here, where X is 70. By the way, why the strips are thick? Because these strips have negligible resistance. Resistance is inversely proportional to the area of cross section. So when it is thick, the resistance is negligible. Therefore, A point and A point, we call this point also as A. This point also as A. Now, I have got null point at 0 point here. From this formula, I have to write X upon R is equal to RAD upon RCD. Let me complete this part first. X upon R is equal to RAD upon RCD. Now, the resistance is rho into length upon area. Similarly, resistance is rho. Now, I call this length as say L. Rho, this length is 100 minus L upon area. That is X upon R. That means rho and rho cancels. A and A cancel. So we get X upon R is equal to L upon 100 minus L. We get this. So we can get this X and R in terms of length. So now what I do is, when I touch the jockey here, L is say 70. So what will be 100 minus 70? 30. When I remove 10 ohms, I got 70. I know one thing. What I know? X is directly proportional to length. So suppose I call, instead of 100 minus L, I call this length as Lx and this length as Lr for convenience. So if X is more, then Lx has to be more. And if R is more, R is less, Lr is less. And I want null point in the middle. So what I do, I remove say 20 ohms. For 20 ohms, I get null point somewhere in the center. Center means where? At 50. What is the meaning of null point? No deflection in the galvanometer. Galvanometer deflection is 0. It is called as null point. And this method is called as null method. We get very good accuracy with null method because there is no current flowing. So at this point in the wire, that is a D point, at this point in the wire, between B and D, there is no current. Is it not fulfilling the condition? Wheatstone bridge principle? When there is no current flowing in the wire, in between B and D, that means X upon R is equal to Lx upon Lr. Suppose I get this point at say, at this point. So I'll get Lx upon Lr. Suppose I get it at 50. Exactly 50. By the way, what is the length of the wire? 1 meter. Means how many centimeter? 100 centimeter. So at 50 centimeter, I get 0 point. Zero current in this branch. That is potential at this point is equal to potential at this point. There is no potential difference. There is no current. So Lx 50, 50. So let me write it here. X upon R is equal to 50 upon 50. Means X is equal to R. What do we get? X is equal to R. R is how much? R is 20 ohms. So this result is fast when you go for 50. So you can always adjust the resistance box values in such a way that you get deflection. Now one more thing you have to remember. Here, resistance box keys have to be very tight. So when you perform the experiment, when you start with the experiment, you have to first confirm whether the keys are tight. So move it in the clockwise direction and make them tight. Then you have to remove something from here. Say 10 ohms, 5 ohms, 20 ohms, whatever. And then what you have to do, touch the jockey at this point. This is the beginning. And adjust the rheostat for full scale deflection. This is the beginning of the experiment. Then afterwards you have to find a null point. You have to adjust in such a way that null point is in the center. Now one more thing I will tell you. By chance if you get the null point away from here so much, that means you have removed a very less value. Because this value is proportional to the length. If you want length in the middle, you keep on increasing this value so that the null point will be shifted at the center. These are the things, if you remember, experiment is very easy. Now, we have to know what is the aim of our experiment. Aim is to find the unknown resistance of the given wire. We don't know the resistance. So, what is X equal to? And second is, what is rho equal to? Rho is called as resistivity or specific resistance. Resistivity or specific resistance. You all know that resistance is directly proportional to length and inversely proportional to the area of cross section of the wire. So we need to find out the diameter of the wire, and we have already found out in last year the instrument to find the diameter of a thin wire, micrometer screw gauge, and we'll find a diameter and then radius. So length upon area. So resistance is equal to rho into length upon area. Rho is the specific resistance of the material of the wire. It is a constant for the given material. It varies for different materials. So this is what. Now what is the aim? Rho is equal to resistance into area is pi r square upon length. So we find, first only measure the length of the wire which is given to us. Say it is 1 meter or 1.5 meter. We'll substitute here whatever resistance we got, say 20 ohms, we write here. Okay. And now we will, in this case, we are writing it as X. Our resistance is X. So I will write here the value X. Pi is 3.142. Radius we have to find out by using micrometer screw gauge, and then length of the wire, and we will get the answer. Now we need to know what is the unit. Unit we can easily find out. Rho, X is in ohm, pi r square, meter square, area, length is in meter. So 1 meter will get cancelled and we get the unit as ohm meter. So whatever value you get in ohm meter is the unit. So this is the experiment we have to do. Thank you very much. This experiment very interesting, and now we can accurately find out resistance of the given wire, and we also know about Wheatstone brick principle. We can solve many problems. Please watch this video very well, and there are other experiments coming up. Stay tuned to the videos. Click the link in the description box. Thank you very much. See you once again.